For each of these compounds, we're going to circle the alpha carbon. We're going to do that in red. So I'm just going to do this one here. Then we're going to circle the beta carbon. So I'm going to circle the beta carbon in blue. Then we will draw alkene products that may form. So I will do that in black. Now the new alkene will form with a new pi bond between the alpha and the beta carbon. If there's more than one alkene product possible, we're going to circle the most stable. So the reason I did that for that one is I need to move this up. So first I'm going to go through all of these compounds and I'm going to circle the alpha carbon. The alpha carbon is going to be the one that has the heteroatom attached to it. You see the X's here to represent our heteroatom. It could be any halogen. At least in our class, we're sticking mostly to halogens for this particular module. So there are our alpha carbons. Our beta carbons are the ones that have the beta hydrogens that can be eliminated. So I'm going to circle the beta carbons now. The beta carbons are next door to the alpha carbons. Didn't realize I was leaving that one hanging. Now this one I wanted to circle here, but this one doesn't have any beta hydrogens. So I'm going to actually circle that one in green because although it is a beta carbon, it doesn't have a beta hydrogen. So the only way this can go is over to the left. So the beta hydrogen, similarly over here, this is a beta carbon though. It just doesn't have any hydrogen atoms. So these are all my possible beta hydrogen spots. So now we can draw our products. Now the product of an elimination reaction is going to be an alkene. The alkene, the double bond, is going to occur between the alpha and the beta carbon. So that would be our product. For C, the ring stays the same. And we form the pi bond here. For D, we only have the one beta carbon, For E, these are chemically equivalent. So I could draw this or I could draw this. They're both going to be named trans 2-pentene. They're the same compound. For F, again, we have some chemical equivalents here. So I could fall to this beta side or I could fall to this beta side. Either way, this is cyclohexene. It's the same compound. For G, however, we do have chemically dissimilar beta carbons. So I could draw my pi bond here, or I could draw my pi bond here. Either way, these are the same compound. I could draw my pi bond here, but let's name this. So we have 1, 2, 3, 4, 5. So this is a 2-pentene with a 3-ethyl. Well, what about this one? 1, 2, 3, 4, 5. This is 2-pentene and 3-ethyl. So it's the same compound. These 3 beta carbons are chemically identical. They will only form the one product. For H, we can only form the one product as well. And we can only form that one product because there's only one beta carbon that has a beta hydrogen. We can't remove a hydrogen that's not there, so this is the only product that we can form. For I, for similar reasons, this tertiary or quaternary carbon here doesn't have a hydrogen to remove. So this is our product. For J, we have dissimilar beta carbons. So here we finally get to one where we can decide which one is more stable. So we have this product and we have this product. This is going to be our more stable product, and it's more stable because it is a more substituted alkene. You see, there are two carbon groups, one here and one here. For this alkene, we only have one carbon group on the one side of the double bond. So this is our more stable, the internal alkene. For K, we could form our alkene to the left, or we could form our alkene to the right. The more stable one is going to be the one that is more substituted, the more stable alkene. This is a tri-substituted alkene. You see the 1, 2, 3 carbon groups, and down here we only have 2 carbon groups on our alkene. And for L, we have 1, 2, 3 beta carbons, so we should be able to form 3 potential products. So we have a methyl group here and an propyl maybe, 1, 2, 3, yeah, propyl group. So that's if I use this beta carbon. So if I use the beta carbon that's on the methyl group, 2, 3, I think I have the right number of carbons, 1, 2, 3, 4, 4. It's sloppy, but it's there. And then the last one, well, I wouldn't accept that on a quiz, so I better do that right. And I put an oxygen. There, that's better. And for the last one, if I use this as my beta carbon, I have a methyl group there, like that. So which of these is going to be the most stable? Well, this is the most substituted. There are 4 carbon groups, 1, 2, 3, 4. Therefore, this is the most stable. On the other ones, we have 2 carbon groups on this side, or on this potential product, and 3 carbon groups on this potential product. And that's why the top one is the most stable. It's the most substituted.